Picture this, a universe in its infancy, not zero, but brimming with entropy, even at the earliest stages we can describe. A plasma of quarks, gluons, neutrinos, particles, and their antimatter counterparts zipping around at nearly the speed of light. This early universe was far from organized, yet was not in a state of complete disorder. Entropy, after all, is not simply a measure of chaos, but a measure of the possible arrangements of the quantum state of a system. Over time, every energy-emitting reaction, every fusion of atomic nuclei, every gravitational collapse of gas into stars would increase the overall entropy of our universe. And today, the largest contributor to this universal entropy: black holes. But here's the real kicker. Oh, you'll find out just soon enough. What's up, my extraordinary and curious folks? Welcome back to another episode of Curiosity Wonderland. I'm your host, Cesar, ready to dive deep into the mysteries of the universe with you. And joining me on this cosmic journey is none other than the insightful Sonia.
Hi, listeners, ready to unravel another mystery with us?
Absolutely. And remember, folks, make sure to subscribe to our channel and hit that bell icon so you won't miss any of our daily episodes. We're here every day at 10, 14, and 20 hours, bringing you the most fascinating curiosities from around the world and beyond. Did the universe start with zero entropy? Not really. This might be counterintuitive, but let's explore it a bit more. The second law of thermodynamics, one of the most unbreakable laws of the universe, tells us that in any physical system where nothing is exchanged with the surrounding environment, entropy, or what we sometimes refer to as disorder, always increases. This rule applies not only to isolated systems within our universe, but to the entire universe itself. So if we compare our universe today to any earlier point in time, we find that the entropy has always risen and continues to rise, with no exceptions, throughout all of our cosmic history. Now, if we go back to the earliest times, to the very first moments of the Big Bang, or even to the epoch of cosmic inflation that preceded and set up the hot Big Bang, we'll find that the universe wasn't in a state of maximal organization at the start, nor was the entropy zero.
Interesting. So it's a common misconception that the universe started with zero entropy or in a state of maximum organization.
Exactly. The universe was far from being maximally organized at the start of the Big Bang. It had a large entropy even at the earliest stages we can describe, during the hot Big Bang, and even before. It's important to note that organized isn't quite the correct way to think about it, even though we often use disorder as a casual way to describe entropy.
That's a fascinating way to look at it. We often see entropy as being synonymous with chaos or disorder, but it's much more complex than that in the context of the universe. It's about the possible arrangements of the quantum state of a system.
Absolutely. And the universe underwent a massive amount of growth and evolution from the hot Big Bang until the present day, and continues to do so. Interestingly, our entire observable universe was approximately the size of a modest boulder some 13.8 billion years ago, but has expanded to a radius of about 46 billion light-years today.
Wow, when you put it like that, it really puts things into perspective, and all this complex structure, growing from seed, imperfections of at least 0.003% of the average density early on. It's truly mind-boggling.
So, the early universe was a crowded place, full of all kinds of particles, including everything from the Standard Model to their antimatter counterparts, gluons, neutrinos, photons, and whatever's responsible for dark matter. Imagine all this, along with any exotic species of particles that may have existed, densely packed into a tiny volume with incredible kinetic energies.
Like a cosmic pressure cooker.
Exactly. And this hot, dense, rapidly expanding universe was almost uniform, with variations of just one part in about 30,000. It took 13.8 billion years for this high-energy state to evolve into the universe we know today.
So it started in a kind of disordered state then?
To our human perception, it might seem so. The early universe was so hot and dense that it prevented composite particles like protons and neutrons from stably forming for the first fraction of a second. Instead, there was only a quark-gluon plasma, with other particles zipping around at nearly the speed of light. However, even in this seemingly chaotic state, there was a significant amount of entropy.
But isn't entropy a measure of disorder?
That's a common way to describe it, but it's not entirely accurate. Entropy isn't as simple as comparing a broken egg on the floor to an intact one on the countertop, or a chaotic pile of clothes to a neatly organized dresser.
So how do we quantify entropy then?
Instead of focusing on concepts like order and disorder, we should think about the quantum state of each particle in the system and the range of states allowed given the energy distribution. What entropy measures is the number of possible arrangements of the quantum state of the entire system. To better understand entropy, let's consider two systems. In the first one, we have a container divided into two, with cold gas on one side and hot gas on the other. In the second, the divider has been removed, and the entire container is filled with gas of the same temperature. Which one do you think has more entropy?
Is it the one with the gas of the same temperature?
Correct. The well-mixed system has more entropy because there are more ways to arrange the quantum states when all the particles have the same properties. Now, think about the early universe. It had a certain number of particles with a specific energy distribution. Most of the entropy at these early stages was due to radiation.
Right, and every time an energy-emitting reaction occurred, the overall entropy of the universe would have to increase.
Precisely. And these reactions included forming a neutral atom, fusing a light atomic nucleus into a heavier one, gravitationally collapsing a cloud of gas into a planet or star, or creating a black hole.
So would it be correct to say that the entropy of the universe is always increasing?
Absolutely. The entropy of the universe has consistently increased through all of its stages. And today, the largest contributor to our universe's entropy is black holes.
Black holes? That's fascinating. I wouldn't have guessed that.
Yes, it's surprising. Given the number and mass of black holes present in our universe today, the entropy has reached a value that's about a quadrillion times as large as it was in the earliest stages of the Big Bang. Fascinatingly, the entropy of a black hole is proportional to its surface area, so larger black holes have higher entropy. For instance, the Milky Way's supermassive black hole alone has an entropy around 1,000 times more than the entire universe in the early stages of the Big Bang.
That's absolutely mind-boggling, and it's making me remember something from my childhood.
Oh, do share.
Well, when I was a kid, I used to love playing with marbles. I had this huge box filled with different types and sizes. One day I tipped the box over and the marbles scattered all over the room, rolling under furniture, into corners, everywhere.
Sounds like quite a mess.
Yes, it was. But in a way, it was also like a mini-universe in chaos, each marble, like a particle, finding its own path and contributing to the overall entropy of the room. Of course, I didn't know about entropy back then, but now that you explain it, it feels like a fitting analogy, doesn't it?
That's a great analogy. In fact, if we continue to consider the universe, it's estimated that in about 10 to the power of 20 years from now, entropy will reach its maximum. Up to 1% of the mass of the universe could end up locked in the form of black holes, significantly increasing the universe's entropy.
So, my marble scattering was like a preview of a far-off cosmic future.
In a way, yes. But remember, all this assumes that the entropy of our universe applies only to the observable universe, which expands over time. If we consider entropy density, or the entropy of the observable universe divided by its volume, we get a different story.
More layers to the complexity, just like my childhood room full of scattered marbles.
It's astounding. Even though the overall entropy of the universe today is enormous, the volume is so large that the entropy density is comparatively small.
It sounds counterintuitive, doesn't it?
It does indeed. It reminds me of an event from last week. I've been exploring different hiking trails, and I went to this vast forest reserve. It was so massive that even though it was teeming with wildlife, at times it felt like I was the only living being there. The density of life, so to speak, was small because of the sheer volume of the place.
That's a great analogy. Interestingly, I had a similar experience. I went to a beach last weekend and it was so expansive that even though there were plenty of people, it didn't feel crowded at all. It was like everyone had their own spacious bubble.
Exactly. Just like in our universe, despite its relentless expansion, the actual calculable entropy of the universe has increased tremendously. When we compare the entropy present in the early universe, at the earliest moments of the Big Bang, with the entropy today, there's a vast difference of about 15 to 16 orders of magnitude.
So just like the beachgoers and wildlife in our stories, the universe is teeming with entropy, only spread out over such a vast expanse that the density seems smaller.
You hit the nail on the head, and this difference will only be exacerbated if we distinguish between the observable universe, which we can see and measure today, and the unobservable universe, which remains largely unknown to us. The universe might truly be infinite beyond what we can see. What a thought, isn't it?
It's truly mind-boggling. It makes our beach and forest experiences seem so tiny and yet so closely related.
Moving on, it's crucial to bear in mind that the Big Bang, while being the origin of our universe as we know it, isn't the very first thing we can sensibly discuss.
So, it's not the absolute beginning of everything?
Correct. It refers to an early set of conditions, hot, dense, almost perfectly uniform, and expanding. Now, to set up the Big Bang, we have evidence pointing to another state preceding it, cosmic inflation.
What's cosmic inflation?
Cosmic inflation suggests that before the Big Bang, the universe was filled with a dark, energy-like form of energy. This energy might have been inherent to a field permeating the fabric of space, or the space fabric itself.
And how did this inflation affect the universe?
As the universe expanded during inflation, it did so exponentially, not at a decreasing rate determined by the falling density of matter and radiation. Each passing moment, a region the size of the Planck length, the smallest physics allowable scale, gets stretched to the size of today's observable universe.
That's an intense expansion.
Yes, it is. This exponential expansion also plays a role in keeping the entropy constant, but dramatically lowering the entropy density.
So it's like the universe is still spreading out?
Precisely. During inflation, the actual entropy of whatever was present in the universe doesn't change that much. It just gets diluted. The initial entropy density changes dramatically during inflation. Any pre-existing entropy in the universe remains, but gets gradually stretched across larger volumes.
So it's like it's thinning out over a vast area?
Absolutely. We don't need a miraculously low entropy state to begin our universe or to kick off the process of inflation. All that's needed is for inflation to arise in some volume of the universe, even a small one.
And once it starts, it just keeps going, spreading the entropy over a larger area.
Exactly. Even if there was a lot of entropy initially, it soon spreads out over a much larger volume. Even though total entropy may be increasing, the entropy density drops to an incredibly low value.
How does that transition from inflation to the Big Bang occur?
When inflation ends, the energy driving the exponential expansion converts into matter, antimatter, and radiation. This conversion causes the entropy within our observable universe to rise dramatically at that moment.
That must be a significant rise.
Absolutely. It rose by about 73 orders of magnitude from the final stages of inflation to the beginning of the hot Big Bang.
And after that?
Over the next 13.8 billion years, as our universe expanded, cooled, and formed atoms, stars, galaxies, black holes, planets, and even humans, our entropy rose by an additional 15 or 16 orders of magnitude.
How does that compare to the initial rise?
All that has happened and will happen over the entire history of the universe is peanuts compared to the biggest entropy growth spurt ever, the end of inflation and the beginning of the hot Big Bang. Even during inflation, with such extraordinarily low entropy, we never witnessed the entropy of the universe decrease. It was only the entropy density that went down as the volume of the universe expanded exponentially.
What can we expect in the far future?
In the distant future, when the universe expands to about 10 billion times its present radius, the entropy density will once again be as small as it was during that inflationary epoch from long ago.
So the entropy density will continue to decrease?
Correct. While the entropy within our cosmic volume will keep on increasing, the entropy density will keep dropping. It will never be as large as it was at the start of the hot Big Bang, some 13.8 billion years ago. In essence, the entropy dynamics of our universe is a fascinating tale of constant rise and dilution. So in a nutshell, the second law of thermodynamics holds that entropy always increases, even in our ever-expanding universe. The idea that the universe started out in a state of perfect organization or low entropy isn't accurate. Instead, entropy has always been present, changing and increasing as the universe evolved.
It's fascinating to think that even during the inflationary state, the entropy of the universe didn't decrease. Instead, the entropy density was diluted as the universe expanded in volume.
Exactly. So our universe isn't a tale of order turning to chaos, but rather a cosmic dance of entropy, constantly rising yet dispersing in a vast cosmic sea. That's one big cosmic dance floor.
That's a great way to put it. It's been an incredible journey, unraveling the mysteries of entropy in our universe. Remember, if you enjoyed this deep dive into the cosmic dance of entropy, make sure to hit the like button, share your thoughts in the comments section, and spread the word about our podcast with your friends.
Yes, please do. We always love hearing from you. But for now, it's time for us to sign off.
Thanks for joining us on this cosmic journey. Until next time.
Until next time, stay curious, folks. I came across this fascinating piece on Big Think titled, "Did the Universe Have Zero Entropy When It First Began?" by Ethan Siegel, published on February 22nd, 2024. Check out the full URL in the video description if you want to delve deeper into the subject. Now it's time for me to sign off. Stay curious, folks.